This video is on residuals. A residual is how far away an observed value is from what is predicted by the regression line. What this means is that the residual is what's left over from the line of best fit. So if we look at this picture down here, we can see that the data points are not directly on the line. So the residual is the space in between the data point and the line. Just as if you were to take a sticker off, you would have leftover pieces. The leftover is residual. So we want to know how closely the data points are to the line. The residual helps us to determine if the line of best fit is in fact the best fit. So we would want to find the residuals by finding the observed values and subtracting the predicted values. The smaller the residual is, the smaller the residuals are, that means that the line of best fit or the equation of best fit fits the data better. The bigger the residuals are shows that you have more of a weaker line of best fit. So the sum of the residuals will be 0 or very close because of rounding. So what it'll look like is when we have our data points, we will try and find a line that fits this data the best. So something like this. We want to find the line, very similar to here, that'll fit this data the best. We will have positive residuals and negative residuals, because when we have the data points that are above the line, these are the positive residuals. All these would be the positive residuals. So these values, combined with our negative residuals, would give us a value of 0. These would be all negative residuals. These values are going to be above and below it, so that they will add to 0. So the residual plot will actually show us if a linear model fits the data the best. If a linear model fits the best. So fits the data the best. You can also use the residual plot to see if an exponential model fits better, if a quadratic model fits better. It all depends on the residuals away from them, and if the residuals are smaller, then whatever regression you did for that would be the better fit. In order to create a residual plot, you would need to have the data put into either a calculator, a Desmos, some type of technology, so that you can create the equation of best fit. So to create a residual plot, we would have plugged these values in to Desmos or into our calculator and actually did the regression formula. This data right here actually gives us the regression equation of y equals 0.455x plus 0.683. This is been done using regression. So on a separate video, you can see how to do regression in Desmos to get this data. So in order to do the residuals, we now have the regression equation that fits this line, but notice that the line does not go through all the data points, but it fits it the best. So to find the residuals, we need to take the observed values and we need to subtract the predicted values. Now using the equation, what we would do is figure out from the line of best fit what the predicted value would be for when we plug in the x value. So we're going to use the x values. So if we were to plug the 3 in for the x value, we would end up getting 2.05. So 2 and 500ths. And again, this is rounding. If I were to plug the 10 in for the x, we would get 5.237. Plugging in the 15 into our regression equation, we get roughly 7.513. Plugging in the 20 into the regression equation, we would get roughly 9.790. Plugging in the 25, we would get roughly 12.067. And plugging in the 30 into our regression equation, our predicted value would be roughly 14.344. Again, this is all a predicted value. This is the actual data we were given. So these are the coordinates that are plotted on this graph. The predicted value, instead of it being at 3, it would be at 3,2.05, which is on this line. And the same thing happens at 10. This would have been at 4, but on the regression equation, it would have been at 10,5.237. So this is the predicted value. The residual is the values that are left over, the space in between from the actual data point to the regression equation. So in order to find this, we take the observed value and we subtract the predicted value. We're going to subtract all these numbers. So 3 minus 2.05 is a positive 0.95. Then 4 minus 5.237 is a negative 1.237. And we can see that this value is below the regression line, and this data point was above the regression line. That's why this one was positive and this one is negative. So 9 minus 7.513 is 1.487, which again is above the data, or the data point is above the line. Next one is below, so we should have a negative. So 7 minus 2.790 is negative 2.79. 13 minus 12.067 is 0.933. And then 15 minus 14.344 is 0.656. And we can see that these are also above it. Now, these data points are very close to the line, which is why this residual is much smaller than the others. We can also see that this data point looks to be the furthest away from the line. And if we look at the residual, we can see that that is the largest value, the absolute value of it. So regardless of the negative tells us that it's above or below the line. But the 2.79 tells us that it's the furthest away from the actual regression line. So these are our residuals. If we were to add these together, it should become 0 or really close to 0 because the values are the space in between. So if we add those, it should become to the line, which would be a 0 value away from the line. So to plot residuals, we actually take these values and plot them on a horizontal line. Because what residuals do when you plot them, it takes this graph right here and it turns it so that our regression line becomes horizontal. So that way you can count up and down to be able to see how far away the actual data point is from our line. So we want to show this on a horizontal line. So if we make our data points at 5, 10, 15, 20, 25, and I'll do another one at 30 because those are our x values. But now our residuals are going to be the y values. So I'm going to count, so this is going to be 0. I'm going to count by halves. So a half, 1, 1.5, 2, 2.5. These are the residuals. And so I'm going to go down to negative half, negative 1, negative 1.5, negative 2, and negative 2.5. I'm going to plot at 3. I'm going to have my residual at 95 hundredths. So my residual will go at around 3 and 95 hundredths, roughly here. Then at 10, it's going to be at negative 1, 2.37, roughly here. At 15, it'll be at 1.487, so almost 1.5. At 20, it's going to be at negative 2 and 79 hundredths. So it's going to be down here. At 25, it's going to be at almost 1. And then at 30, it's going to be at almost 66 hundredths. About here. Now, if I were to look at this, and I were to turn this picture sideways to make it more horizontal, these dots are going to be about the same distance away. Well, they will be the same distance away if I were to have my same scale. So all a residual does is so that you can now count this distance away, as in these distances away diagonally, because you cannot count up and down on a diagonal line. So what it's doing is it's turning it so that I can count up to the horizontal line to see the negative and the positive values of the residuals. That's how you create the residual, and you can do this with technology to plot your residuals, especially on Desmos, which allows you to see both the regression equation with the data points along with your residuals. Again, the smaller that the residuals are to each other, or to 0, the closer that they are to 0 as you go through them, then the better the fit is. This is a pretty good linear regression. The correlation coefficient would be strong. This would be a positive, strong relationship, and our residuals are much closer to 0, so that means that our regression equation fits very well for this data.